Okay, imagine looking out at the night sky, all those stars, galaxies, that huge cosmic web. And now get ready for this really mind-bending idea. What if all of that, everything we see, our entire universe, isn't, the whole story?
What if it's actually tucked away inside something else?
Exactly. Specifically, what if our cosmos is like contained within a black hole that exists in some much bigger, maybe older parent universe?
It's definitely an audacious thought.
It really is. And that's the hypothesis at the heart of this deep dive. We've got a stack of sources here, some pretty fascinating research papers, articles that explore this territory.
Right. So our mission today is to really unpack these sources. We're going to dig into this idea, sometimes called black hole cosmology. We'll look at the theories behind it, the physics tools used to think about it.
And also the skepticism, right? Why mainstream science isn't quite jumping on board.
Absolutely. We need to understand what the sources say about how it might work, what it implies, and crucially, how it stacks up against our standard picture of the universe.
Because this idea, it fundamentally challenges the conventional Big Bang model. It opens up these wild possibilities, maybe even multiverses. So yeah, let's jump in and see what the sources actually tell us about this complex but, wow, captivating concept.
Okay, so the core proposal, as it's laid out in the sources, is basically that the universe we live in is the interior of a truly enormous black hole, one that formed in another parent universe.
And this isn't totally brand new, right? I think the sources mentioned variations have been kicked around for a while.
That's correct, yeah. Decades in some forms.
So is the idea that the edge of our observable universe, the cosmic horizon, is that somehow analogous to the event horizon of this parent black hole?
That's the connection some proponents make. And it's interesting, some sources highlight what might be a numerical coincidence.
Oh, what's that?
If you calculate the size of an event horizon for a black hole that has the mass energy equivalent of our observable universe, well, it turns out to be roughly the same size as the Hubble radius, the radius of our observable universe.
Huh. That that is a striking alignment, at least on the surface. But is it just, a coincidence?
Well, the sources are pretty clear that many, probably most, scientists think it is just that, a coincidence. Correlation, not causation.
Okay.
But for the physicists exploring this hypothesis, it's, let's say, a suggestive starting point. And importantly, the way they propose our universe began inside this black hole is different from the standard Big Bang singularity.
How so? How's it different?
Instead of everything collapsing down to an infinitely dense point, which is mathematically problematic, this scenario suggests something called a big bounce.
A bounce. So matter falls in, gets incredibly dense, but instead of hitting a singularity where physics breaks down, it rebounds.
Exactly, that's the idea. One version, which gets discussed quite a bit in the sources, uses a modified theory of gravity Einstein-Cartan theory.
Okay, what does that add?
It includes an effect linked to particle spin called torsion. And the idea is, at the absolutely insane densities you'd find inside a collapsing massive black hole, this torsion could create a kind of repulsive force.
Ah, like pushing back against the crush.
Precisely. Powerful enough to prevent a true singularity from forming. So the matter collapses to an extremely high but finite density, and then this repulsive force makes it bounce outwards violently.
So in this picture, our Big Bang wasn't the absolute beginning of everything, but more like a specific event, this bounce happening inside a black hole somewhere else.
That's the narrative this hypothesis paints, yes. From our perspective, inside this newly expanding region, it looks just like a Big Bang rapid expansion from a hot, dense state.
But from the outside, in the parent universe.
So someone there might just see a black hole form and, well, sit there. Or collapse. The idea gets more complex here, suggesting the collapsing interior might smooth out into a type of wormhole, an Einstein-Rosen bridge.
Connecting the parent universe to ours.
Potentially. Connecting the parent universe to this new baby universe.
Mm-hmm.
Our Big Bang would then be the white hole end of that bridge, the part expanding outwards.
A white hole. Isn't that the time-reversed version of a black hole? Stuff only comes out.
In classical theory, yes. Though stable white holes are generally seen as pretty unlikely, maybe even non-physical in our universe. But the argument is that behind the parent black hole's event horizon, maybe such an emergence is possible.
And this leads to that idea that maybe every black hole in our universe could be doing the same thing, spawning new universes.
That's the implication. It opens the door to this potentially recursive multiverse structure in the universes, nesting like Russian dolls, constantly generating new ones. It's a very compelling mental picture.
It really is. But okay, let's get practical. How on earth could we test this? Is it testable?
And that is the massive hurdle. The sources really hammer this point home, because if our universe emerged from behind the event horizon of the parent black hole, well, we're causally disconnected.
Right, the event horizon is like a one-way street. Information falls in from the parent universe.
But nothing gets back out to the parent universe from inside the black hole. And critically, no information can get in to our universe from the parent after that initial formation event, that bounce.
So we can't just, like, look for signals or relics from the parent universe directly.
According to this model, no. That causal isolation is convenient for explaining why we don't see a parent universe, but it makes the whole hypothesis incredibly difficult to verify, or falsify for that matter, through direct observation.
Okay, direct observation is out. But what about indirect signs? Has anyone looked for, I don't know, subtle fingerprints on our universe that might hint at this kind of origin?
Yes, absolutely. There have been attempts, though we're definitely on the speculative frontier here. One area people look is cosmic anisotropy.
Meaning deviations from the idea that the universe looks the same in all directions.
Exactly. Our standard Big Bang model, especially with inflation theory added, predicts an incredibly smooth and isotropic universe on large scales. And observations like the cosmic microwave background, the CMB, strongly support that. It looks remarkably uniform.
Okay, but how does the black hole idea relate?
Well, if our universe was born inside a spinning black hole, you might naively expect it to inherit some kind of preferred axis, maybe a direction of rotation or alignment imprinted on it.
Ah, right, like swirling water going down a drain leaves a pattern.
Something like that. And some studies have looked for this. The sources mentioned work by Lior Shamir, for instance. He analyzed the spin axes of distant galaxies using JWST data, I believe.
What did he find?
He reported seeing an unexpected pattern, a sort of preferred direction or anisotropy in how these galaxies are spinning. And he suggested this could potentially be a relic, a signature of our universe originating from a rotating structure like a black hole.
Wow, okay, if that were confirmed, that would be huge. A serious challenge to the standard model's assumption of isotropy.
It absolutely would be monumental. However, and this is big, however, the sources also stress this finding is, well, preliminary and quite controversial.
Right, controversial.
The sample size of galaxies Shamir used was relatively small. Other analyses, using larger data sets, haven't replicated this finding. They don't see this preferred rotation. So mainstream cosmologists are, understandably, very cautious.
Extraordinary claims require extraordinary evidence, right?
Precisely. And the evidence for this large-scale anisotropy just isn't considered robust yet. The overwhelming data, especially from the CMB, points very strongly towards isotropy.
So the search for clues continues, but right now the evidence leans heavily towards the standard picture, not the rotating black hole origin.
That seems to be the consensus based on the sources, yes. The isotropy predicted by the standard model holds up extremely well.
Okay, let's shift to the theory side again. How do physicists even compare the geometry of a black hole interior to our expanding universe? What tools show the difference?
Right, this gets into the mathematics of space-time itself, using what are called metrics. General relativity describes gravity as the curvature of space-time, and the metric is the mathematical tool that tells you how to measure distances and time intervals within that curved space-time.
So you compare the metric for a black hole to the metric for our universe.
Exactly. For a simple, non-rotating black hole, we use the Schwarzschild metric. For our universe, assuming it's broadly the same everywhere and in every direction, homogeneous and isotropic, we use the Friedmann-Robertson-Walker metric, or FRW metric.
And what's the key difference these metrics show us?
This is where it gets a bit mind-bending, but it's absolutely crucial. The Schwarzschild metric for the black hole shows that outside the event horizon, space is space and time is time, pretty much as we expect.
Okay.
But inside the event horizon, things get weird. Space and time essentially swap roles. The radial coordinate distance from the center starts behaving like time, and the time coordinate behaves like a spatial dimension.
Whoa, what does that mean practically?
It means everything inside the horizon is irresistibly compelled to move towards the center, towards the singularity in its future. Just like we, out here, are compelled to move towards tomorrow. You can't avoid hitting the singularity once you're inside.
Okay, I think I follow. How does that compare to the FRW metric for our universe?
The FRW metric describes an expanding universe. It has a scale factor that grows with cosmic time. It also classically has a singularity, the Big Bang singularity. But here's the key difference. That singularity is in the past. of all events.
Ah, so it's not a place you fall into in the future.
Exactly. It's a moment in time in the past from which everything expanded away. The black hole singularity is a destination in space, or rather, a future point unavoidable once inside, while the Big Bang singularity was a moment in time.
One is space-like, a location you reach. The other is time-like, a moment everything emerged from.
You've got it. Fundamentally different natures. And as astrophysicist Paul Sutter points out in some of the material, inside a black hole, everything is crushing toward the central singularity, whereas our universe is, of course, expanding away from its initial state.
So that fundamental difference is a major problem for the simple idea that we're just inside a regular black hole.
It is. It's a core reason why the black hole cosmology hypothesis needs those extra ingredients we talked about, like the big bounce mechanism, maybe needing new physics like Einstein-Cartan theory to change the interior behavior. It has to somehow transform from a collapsing state heading to a future singularity into an expanding state emerging from a past event, like our universe appears to be.
How do physicists visualize these really strange spacetimes? Is there a way to map them out?
Yeah, Penrose diagrams are incredibly helpful here. They're clever diagrams that manage to map potentially infinite regions of space-time onto a finite picture while still preserving the causal structure.
Causal structure meaning?
Meaning, they clearly show which events can influence other events. Critically, light rays always travel on 45-degree lines in these diagrams.
So it's like a map showing cause and effect, pathways, and boundaries.
Precisely. And a Penrose diagram for a standard black hole clearly shows the event horizon as a boundary. It shows the singularity as a future boundary inside the black hole.
And it shows the disconnect.
Yes, it visually reinforces that causal isolation. Once a path crosses the event horizon going in, all possible future paths, including light rays at 45 degrees, inevitably hit the singularity, or the bounce point in the modified theory. You simply cannot draw a valid path back out across the horizon to the original universe.
So the diagram helps visualize why the baby universe, born from the bounce, would be cut off from the parent.
Exactly. It makes that causal separation very clear. From our perspective inside, the bounce event would effectively be our universe's starting point of expansion, lying in our causal past, much like the Big Bang in the Standard Model.
Okay, let's talk about entropy. That's always a big topic in cosmology. And black holes, the arrow of time, increasing disorder. How does that fit in?
Thermodynamics is definitely key. We know black holes have enormous entropy, related to the area of their event horizon. It's a measure of disorder or hidden information. Our universe also clearly has increasing entropy. That's basically why time flows forward for us, things break down, order turns into disorder.
And there's that puzzle about the early universe, right? Roger Penrose talks about this. Why was the very early universe so incredibly ordered, gravitationally speaking? It was dense, but very smooth.
That's a huge mystery in standard cosmology, yes. That initial low gravitational entropy allowed structures like galaxies to form later as gravity pulled things together. Where did that initial smoothness come from?
How does the black hole bounce idea handle this entropy question?
Well, in this model, the bounce event itself would be incredibly energetic, creating a hot soup of particles and radiation. That would represent a high entropy state in terms of matter and radiation. The arrow of time inside the new universe would then naturally point forward as it expands and cools after the bounce.
But does it solve the initial low gravitational entropy problem?
Not automatically, no. From the parent universe's view, forming the black hole likely increases overall entropy. But explaining the specific smoothness, the low gravitational entropy of our early state, would probably still require some specific mechanism within the bounce model itself. It doesn't just fall out for free.
And what about the information paradox? The idea that information falling into a black hole might be destroyed, violating quantum mechanics. If that information somehow helps create a new universe, is it lost?
Yeah, that connects to one of the deepest, still unsolved problems where gravity meets quantum mechanics. If this black hole cosmology model were correct, it would somehow need to be consistent with the principle that fundamental information isn't truly lost. That's highly speculative. How information might be preserved or transferred across universes in such a scenario is really tangled up in the search for a full theory of quantum gravity. We just don't have the answers yet.
Okay, so summing up the story. It involves changing gravity, swapping a singularity for a bounce, maybe using wormholes, and it touches on deep puzzles like entropy and information. How does it actually stack up against our current, best standard model of cosmology?
Based on everything in the sources, it's fair to say it's considered highly speculative compared to the standard lambda CDM model that's the Big Bang, plus dark energy and cold dark matter, usually incorporating cosmic inflation early on.
And the standard model is successful because...
Because it's just incredibly good at explaining a huge range of what we actually observe. Things like the near-perfect uniformity, but also the tiny temperature fluctuations in the cosmic microwave background, the way galaxies are distributed in giant clusters and filaments, the amounts of light elements like hydrogen and helium created just minutes after the Big Bang.
It provides a consistent story for how the universe evolved.
Exactly. It doesn't necessarily explain what caused the Big Bang itself, that initial moment, but it gives us a powerful and well-tested framework for everything that happened since then.
And the black hole hypothesis tries to explain that initial moment.
It does offer a potential origin story for that initial state, suggesting it came from a process within a pre-existing parent universe. But as we've seen, it requires new, unproven physics like torsion and Einstein-Cartan theory. And it introduces these elements like the parent universe and causal isolation that make it extremely hard to test directly.
So the similarities it points out horizons, singularities aren't seen as that compelling by the mainstream.
According to the sources, those similarities are often viewed as more superficial than fundamental, unless you invoke that new physics. The basic geometry and causal structure of a standard black hole interior just don't match our expanding universe. As Paul Sutter apparently put it, the observational evidence we do have points strongly towards the standard expanding FRW universe, not the inside of a black hole, at least within the physics we currently trust.
Are there other ideas floating around about what happened before the Big Bang or instead of a singularity?
Oh yes, definitely. There are other alternative models that also try to avoid the initial singularity. You hear about bouncing universes or cyclic models, maybe explored within frameworks like loop quantum cosmology or ekpyrotic cosmology.
How are they different from the black hole idea?
Those other bounce models often picture the entire universe contracting down and then re-expanding. It's like one universe going through cycles. The black hole cosmology model is more localized. A specific region, a black hole interior, bounces and becomes a new, distinct universe that branches off from the parent.
So it leans more towards a multiverse.
Yeah, it fits more naturally with a branching or nested multiverse picture rather than a single cycling universe.
Yeah.
But just like the black hole idea, these other alternatives also face that huge challenge, finding clear, compelling observational evidence that can really distinguish them from the standard inflationary Big Bang model, which just works so well right now.
Okay, so we started with this really audacious hypothesis. Our universe might be inside a black hole. We've walked through the theoretical bases, needing a bounce, modified gravity, maybe wormholes, the whole causal isolation problem.
Right, and we looked at the tools like metrics and Penrose diagrams that show the geometric differences, unless you add that new physics, and touched on how it intersects with deep questions like entropy and information.
And the takeaway, based on the sources, seems to be that while it's a truly fascinating idea, scientifically speaking, it's still very much on the speculative fringes.
That sums it up well. It requires physics beyond our standard, well-tested theories, and crucially, it just lacks the kind of strong observational evidence that would make scientists seriously consider abandoning the standard Big Bang model, which is incredibly successful.
Those apparent similarities, horizons, singularities, they kind of dissolve when you look closely at the fundamental geometry and causality, unless that speculative new physics is doing the heavy lifting.
Exactly. The physics has to fundamentally change the nature of the black hole interior for the analogy to hold.
So why even spend time exploring ideas like this if they're so speculative and hard, maybe impossible to test?
Well, because this is how science pushes forward. Thinking about these out-there possibilities forces us to question our most basic assumptions about reality, singularities, the beginning of time itself.
It stretches our understanding.
Definitely. And it highlights these amazing potential connections between the physics of the incredibly small and extreme, like inside a black hole, and the physics of the absolutely largest scale, the whole cosmos. That nested Russian doll image is powerful conceptually. It expands our imagination and really underscores how much we don't know yet.
That's a great point. It reminds us there are still huge mysteries.
Maybe here's a final thought, drawing from the sources. The narrative is incredibly compelling, isn't it? This idea that maybe our own black holes are seeding new universes, or that we ourselves emerged from one in some other cosmos, it's almost poetic.
It has a certain appeal, yeah.
But the sources consistently emphasize that science, in the end, has to follow the evidence. And as of right now, Pretty much all our cosmological measurements, the detailed maps of the CMB, the way galaxies cluster, the expansion rate, they all suggest our universe looks and behaves far more like the standard expanding Big Bang model describes it than like the interior of a black hole.
The data just doesn't point that way currently.
Not currently, no.
But the story isn't finished, right?
No.
Exploring these ideas, even if they turn out to be wrong, is still valuable. It keeps that curiosity burning, makes us test our foundations, and just reminds us how vast and, frankly, weird the cosmos might be. There's still so much to figure out. Definitely keep pondering those big questions.